Well, grab your pens and pencils and open your notebooks and strap on your seatbelts, because this is going to be a fairly long introduction lecture on Unit 5.3 on our study of periodic motion. And in this video lesson, I want to make a link between what we finished up, Unit 5.2, in our study of gravity, and the current unit of study we're just beginning on the study of objects that vibrate back and forth. So I've written Gauss's law for gravity, and hopefully this is familiar to you from our last unit of study. It presents the idea that the total gravitational flux through an imagined surface only depends on the amount of mass that lies inside of the Gaussian surface. If this seems a bit sketchier for, and that's okay, we can get away without digging into that equation too deeply. It's probably more important to note the shape of this graph. This is a graph of gravitational field strength compared to distance from the center of the Earth. And we know that beyond the surface of the Earth, gravitational field strength drops off as an inverse squared law, as indicated by the blue portion of this curve. And it's only recently that we derived this equation that tells us how gravitational field strength increases from the center of the Earth up to the surface of the Earth in a linear fashion. And we're going to rely on this expression in order to investigate the periodic motion that results if somebody were to follow this hypothetical scenario. What if you dug a hole to the other side of the Earth and jumped in? What sort of motion would you have? Well, gravity would pull you and accelerate you toward the center, but then what happens when you reach the center? At that point, gravitational field strength is equal to 0. That's this data point on our graph. So does that mean you immediately come to rest at this point? Certainly not. By the time you get to that point, you would have reached a large velocity, and your inertia would carry you on. Now, how fast would you pop out the other side? Well, it turns out your motion would be periodic, meaning there'd be a definite amount of time that it takes to go from the point where you jumped in down to the other side, and then the force of gravity pull you back in the other direction, have your inertia make you overshoot the central point and back to where you dove in. That would be one full cycle, and the time it takes for the second cycle would be just as long as the time it takes for the first cycle, and so on. So the period, what we call capital T, the period of vibration or oscillation, would be a fixed value, and it wouldn't change as you go from the first cycle to the second cycle to the third cycle, and so on, each cycle being a there and back journey to the place where you jumped in. So let's see, what if we make a free body diagram when this person who jumps into this tunnel to the other side of the Earth, make a free body diagram when they reach this position? Well, there's only one force acting on them, and that's the force of gravity pulling toward the center. Let's see now, how about this? If we know gravitational field strength, then it's easy to get the force of gravity. The force of gravity is just the mass of the object multiplied by the field strength, and the gravitational field strength is universal constant times the mass of the Earth divided by the full radius of the Earth cubed, and then multiplied by whatever current position the object has. So the force is equal to G mm over r cubed times r. All right. Let's turn this picture on its side. There's the tunnel going to the other side. There's the central point, and let's imagine this position right here. Now, we'll make a frame of reference where anything to the right is positive, and we'll put our origin right here. So instead of considering this as an r-axis, we can consider it as an x-axis. F equals g mm over r cubed times x. And we'll say x equals 0 at the center of the Earth. So when the object is right here, gravity is pulling toward the center. So the force is in the negative direction when the position happens to be positive, and vice versa. This person jumped in from over here. They fall to the center of the Earth, continue moving. The pull of gravity slows them down. They reach this side, and the pull of gravity accelerates them back toward the center, and they overshoot it and come back to here. So at some point in the cycle, the object will be at this location, but the pull of gravity will be positive, but only when the position is negative. So I'm just trying to point out that the force always has the opposite sign of the position. So yeah, I think we should really write this equation for force as negative g mm over r cubed times x. By Newton's second law, we replace force with ma. So ma is negative g mm over r cubed times x. But a is dv dt, which in turn is the second derivative of position with respect to time. So how about this? Mass times the second derivative of position with respect to time is equal to negative g mm over r cubed times x. So lowercase m cancels out. So lowercase m is the mass of the object that's falling through the center of the Earth. Capital M is the mass of the Earth itself. So now we've got this expression, the second derivative of position with respect to time is equal to negative, well, this is all a bunch of constants, g, mass of the Earth, and radius of the Earth cubed. Those are all constants, and then times x. I should have said at the outset what we're really looking for with all this mathematical derivation. We referenced the idea that it's going to take a certain amount of time to complete one vibration. So the motion varies with time. At any instant, the exact location of the object isn't known unless we can come up with some sort of equation or formula that tells us how position varies with time. So since we've turned it on our side and made the r-axis more like an x-axis, what is the position as a function of time? Well, with all the mathematical derivation we've done up to now, we might be able to get an expression, but we have to scratch our heads a little bit and think about it. Are there any functions that describe position where if I take not just the first derivative, but I take the second derivative? Are there any functions where you can take the second derivative and in doing so get a negative constant multiplied by the very function you're taking the second derivative of? A couple of different equations come to mind. What if the position of the object falling through the center of the Earth was described by this equation? What if it was equal to e to the some constant times t? Let's make that a guess. And now we've got to take the first derivative, dx dt. So this would be a way of describing the velocity of the object as it falls through the Earth. Well, then that would be equal to c times e to the ct. And then the acceleration would be the second derivative. And this would be c squared e to the ct. However, e to the ct, that's just the function x that I guessed at in the first place. So we find that the second derivative of position with respect to time is equal to some constant squared times x itself. Hey, that looks kind of like this. Taking the second derivative of the function is giving us, well, a constant squared itself is a constant. Here's the only problem. It didn't give us a negative constant times the function. I'm not trying to waste your time, but I'm going to guess again. What if the position of an object falling through the center of the earth varies according to this expression? X equals, how about x maximum times e to the negative ct. Let's take the first derivative. This would give us negative c x max e to the negative ct. Let's take the second derivative. This would give us, positive c squared x max e to the negative ct. Now, x max times e to the negative ct is just x itself. So once again, we almost got what we were looking for. We guessed at an expression that describes position as a function of time. We took the second derivative of it, and the end result was a positive constant multiplied by the very function we were taking the derivative of in the first place, and so we still didn't get the negative sign we were hoping for. So maybe you can make a better guess. Some of you might be a step ahead of me on this one. If you've taken any courses in differential equations, then you know how this proceeds. We're just going to keep guessing until we find a guess that satisfies this kind of relationship. What about x equals x maximum cosine some constant times time? What would we get when we take the first derivative of that? Yeah, we'd get negative constant x max sine constant times t. And what if we take the second derivative? Well, I think we're onto something here. Now we're going to get negative c squared x max cosine constant times time. And all of this is just x. Hey, we did it. The second derivative of position with respect to time would be equal to negative some constant times x. So this expression matches this expression as long as the constant is of the correct value. If I copy, I can paste this down below so we can see the two side by side. Clean this up a little bit. Okay, do you see the comparison? We know this has to be true, and based on our guess, we have an equation that looks very similar. The second derivative gives us a negative constant times the very function we're taking the derivative of. This seems to agree as long as the constant is equal, or at least as long as the constant squared is equal to, as long as the constant squared is equal to gm over r cubed, meaning the constant must be the square root of gm over r cubed. Okay, so our guess was position, here was the correct guess, that position is equal to some maximum position times cosine of an unknown constant times t. Well, now we know what the constant must be. So we guessed x equals maximum value of x cosine of some constant times t, but that constant is the square root of gm over r cubed. Now what's this x maximum? Well, that's pretty simple. I certainly know what the minimum value of x is. The minimum value of x is the position that the object has right when it's at the center of the Earth. So what's the maximum value? Well, the maximum value is here at the extreme end, but that's when x is just equal to the radius of the Earth itself. So this would be a perfect guess. If position as a function of time is described by this equation, radius of the Earth multiplied by cosine of, here I'm going to change the language here and say cosine of omega t, and now this is only valid so long as omega is equal to the square root of gm over r cubed, then we've done it. So if we were to graph the position of the object falling through the center of the Earth as a function of time, then at time t equals 0, the position is r, and then it graphs just like cosine. And so, sure, if the person jumps in from this side, then at time t equals 0, their position is r, and then a quarter of a cycle into the motion, they reach the center of the Earth, and that corresponds to this point on the graph. And then half a cycle into their motion, they're over on the opposite side, where x would be equal to negative r, and that's this data point. 3/4 of a cycle, they're back at the center of the Earth. There's that data point. And finally, after one cycle, they return to the position where they jumped in, and then from there on, it would just continue to repeat with the same period of oscillation. Now, wait a minute here. I want to take a closer look at this. Omega is a number of radians per second, and there are 2 pi radians in every cycle. Think of a unit circle. If an object's moving around with uniform circular motion, one cycle is one complete lap around the circle, and so the angular displacement in one full cycle is 2 pi radians. So yeah, there are 2 pi radians in every cycle. Okay. So we can say omega is 2 pi radians in an amount of time, capital T, known as the period. And so the period is equal to 2 pi divided by omega. For us, omega is the square root of gm over r cubed. So another way to express this is to say t is equal to 2 pi times the inverse of omega. So t would be 2 pi times the square root of, well, if omega is the square root of gm over r cubed, then the inverse of omega is the square root of r cubed over gm. So t is 2 pi times the square root of r cubed over gm. Do you see anything interesting here? I hope you see it. This is the exact same equation for the period of a treetop orbit. This is fascinating. The result is, if you were to try to perform a race, go to the top of Newton's Mountain. Remember that one? And at the base of Newton's Mountain is a hole that goes to the other side of the Earth. Now you project something slowly or too slow from Newton's Mountain, it crashes into the Earth. But if you project it with a velocity equal to the treetop orbit, for the Earth that's 7,900 meters per second, and the object orbits around, just barely clearing the treetops, and returns to the top of Newton's Mountain in a time of about 90 minutes. But that time is given by the equation 2 pi times the square root of r cubed over gm. We've derived this multiple times in our previous unit 5.2 on universal gravitation and satellite motion. So here's the race. At the very instant you project the object tangentially from the top of Newton's mountain, I want you to drop something into this hole. The time it takes this object to fall through the center of the earth and reach the opposite side would exactly match the amount of time it takes for the treetop orbit to go halfway around. That's half a cycle. And so they'd almost hit each other right here. And then the object falling through the center of the earth would reverse direction and come back up as the treetop orbit continues on, and by the time it returns to the place where you dropped it in this hole, the satellite would have returned around. They share the exact same period because you notice these equations are exactly the same. So this is our first investigation into a type of motion that shows an object that keeps following the same path over and over. Once the object dropped into this hole returns, it's just going to fall back down again, come back up again, and it's going to oscillate. Or you can say vibrate. Either way. And the period of that vibration is dependent on some physical properties, most notably the mass of the Earth and the radius of the Earth. So if you were to do the same thing on the moon, for example, it would have a different period, but the only physical parameters that determine the time it would take to fall through the center of the Earth for a full cycle are radius and mass. In our next unit of study, well, in this same unit, but in our next video lesson, we're going to present another object that has this same type of behavior. If you were to take a mass and attach it to an ideal spring with a stiffness of K, if the spring is neither stretched nor compressed when the mass is at this position, then we'll say the mass is in its equilibrium position. And as a thought experiment, I want you to try to imagine what would happen if you pulled the mass back a little farther. And so you give it some initial displacement. We'll call it x naught. And if you release it from rest, what happens? Well, it's going to want to return back to the equilibrium point, but because it gets there with some velocity, its inertia carries it past that point, and then the spring for a moment will be compressed. It's going to compress as much as it will. The velocity will reach zero, and then the object will return back the other way, and probably all the way back to where you let it go. In fact, this reminds me of another type of motion that we've studied. When we were studying the law of conservation of energy, we showed that a pendulum, if you take a heavy object and attach it to the end of a string or a cord or a rope, and then you pull it back, giving it some initial angle, maybe we'll call that theta naught. When you release it, it doesn't just immediately come to rest at the equilibrium position. It swings to the opposite side before reaching a velocity of zero and then coming back again. So the time it takes to go from the point of release to the opposite side and back again is one full period of motion. And the time it takes for a mass on a spring to compress to the other side and then come back to where the spring is stretched out is one full period of motion. Well, all of these types of motion have something in common. The pendulum, the mass on a spring, and this hypothetical case of an object dropped and falling through the center of the Earth all represent not just periodic motion, which can also be named as oscillatory motion, but they satisfy a special subset of that periodic motion known as simple harmonic motion. And so much of our study in this unit will be dedicated to an investigation of the behavior known as simple harmonic motion. Thanks for watching. Stay tuned.